Hello and welcome to this Innova Systems webinar on assembly validation tools. If I jump into SolidWorks, we're going to have a look at the assembly validation tools. First of all, most of them are found on the Evaluate toolbar: interference detection, clearance verification, hole alignment, measure, and mass properties. I'm just going to jump into these very quickly to show you some stuff that's new in 2013, and we've got sensors and assembly expert. But before we start working our way through this lot, I want to show you some additional features with the Move Component tool. So Move Component tool, free drag, it's what you use when you're dragging stuff around within your assembly, repositioning components, whatever it happens to be. But there's a couple of other items. There's collision detection, which I'm going to show you in a different assembly. And there's also dynamic clearance. So dynamic clearance allows you to check what the clearance is going to be between two items. Now first of all, what I'm going to do is I'm just going to clear away some components to make things a little bit more visible. And then we're going to choose dynamic clearance between my rod end, it'd help if I clicked in the box, rod end and my arm. We can also choose to set the distance, which is going to be the minimum clearance between these items. Now I'm going to set it to 0 to begin with, just so we can see the full range of possible motion. And then we're going to resume drag. So when I click on it, I can drag it. We can see there's a dimension on the screen, and as we move, that dimension will update. And we can see it comes around to a final value of about 18. Now the number continues to change because this is what the dimension would be if my parts weren't constrained by mates. So we can see it finishes around 17.5, 18. Now if I now change the minimum clearance, and let's set that to say 22, and retry the movement, we can see that our part will stop when the dimension reaches 22. So there we go, and we lose part of our movement. So this becomes a really easy way to see how your parts are going to move with the clearances you expect and want between them, and getting a dynamic update on what the actual distance is between them. So that's showing you dynamic clearance. What I'm going to do now is I'm just going to jump into a different assembly, one which I hope you're all very familiar with, and show you collision detection. So we turn on collision detection. We can then choose whether we want to check between all components. Depending on the size of your assembly, you may want to limit it to specific components, or if you know certain things are going to hit or already in a colliding state, then you might want to exclude them from the study. We can choose to stop at collision, and we can also choose to highlight the colliding faces and play a sound. So I'm going to grab hold of my handle and I'm going to turn. So also demonstrating another 2013 feature where you can pick your own sounds for errors within SolidWorks, which is very exciting. So as we move our part, we can see that the faces collide. As they collide, they go blue, and the movement stops. I can't move any further. So it becomes a really nice way of showing what's happening within your assembly and what's going on. So I'm going to close that and go back to the main assembly. So that is some new or additional items with the move feature. Let's turn everything back on. We're now going to move to the Evaluate tab and start on the left and work our way through. So we're going to start with interference detection. Interference detection is checking whether parts are coincident or overlapping with each other, because SolidWorks doesn't stop body A being inside body B. It just uses interference detection to tell you that's going to happen. But before we hit calculate, I'm just going to have a look at some of the options. So we've got treat coincidence as interference. So if things are touching, SolidWorks is going to assume that they're actually overlapping and tell you about the contact. In this assembly, it's designed very compactly, so there's a lot of things are actually in coincident with each other. So I'm going to turn that off just because I'd get a vast number of results. We can choose to show ignored interferences. So this is if we've ignored them previously, we can choose to show them again now. We can choose to treat sub-assemblies as components. I'm going to turn that off so that we can see all of the interferences within this. But basically that means that you can do your interference study at a sub-assembly level, make sure you're happy with that, and then you can ignore anything within the sub-assembly, so you just treat the sub-assembly sort of as a big block. Include multi-body part interferences if you do a lot of weldments, for example, or you do a lot of multi-body modelling, then this enables you to see whether body A is colliding with body B within the part, as well as the overall part colliding with anything else within the assembly. This isn't modelled that way, so I can leave that off. We can choose to make interfering parts transparent. This is kind of handy in this tool because it highlights the volume that's interfering in red, and if they're transparent you get a really nice idea of how much of a part is interfering. create Fastness folder and create matching cosmetic threads folder are sort of an either or option. The create matching cosmetic threads folder is new in 2013. The create Fastness folder basically says, is this a toolbox fastener? If it is, ignore it. End of. The create matching cosmetic threads folder says, if you've got a hole with a cosmetic thread and you've got a part with a cosmetic thread on the outside of it, then that you are expecting those to overlap, because the hole will have the smallest diameter and the part will have the largest diameter, so there's going to be an overlap over the pitch. And what this does is it ignores those components off into a separate folder to deal with. There's a little bit of overlap, but what happens with the cosmetic threads folder is if there's a collision with the end of the bolt, for example, or the head of the bolt is colliding with something, you'll get to see that. With a fasteners folder, that wouldn't show up. There's a really nice demo of this cosmetic threads folder usage from the customer day on the website, so if you want to have some more details, go and check that out. Finally, we've got ignore hidden bodies and components, and that's basically just saying hide away or ignore everything which I'm not using. And then finally, what do you want everything else to be? And I've set it to wireframe, just enables you to see into the model a little bit more clearly. So I'm going to hit calculate. Now, within my sub-assemblies, there's a whole load of little bits and pieces which are interfering. So I get a really large number of results. So what I'm going to do is I'm going to choose to treat sub-assemblies and components and recalculate. This takes less time to calculate because there's less going on, but also gives me a much more usable list. So we've got an interference here. We've got an interference here. We've got a third interference over there. We've then got a very small interference here, and finally an interference over there. Now these three look as though they're all caused by a bolt, and in fact we can actually go into it and have a look, and we see the interference between the arm and that fixing. This is between the arm and the fixing again, so it's the top and bottom of the arm. And then finally between the link and that fixing again. So the problem's clearly with the fixing. So if I come out, and I'm just going to collapse all of that and find my fixing, and I'm going to configure that so it looks like it's been made too big in diameter. So we'll shrink that down, and then we'll come back in and have a look at interference detection again. Again, we're going to treat sub-assemblies as components, and we're going to calculate. So now we've only got two items. So very quickly, interference detection has enabled you to identify a part which is causing a problem and fix it. So we've now got two interferences left. This one is between an O-ring and a rod end. O-rings, sort of by their nature, you'd expect them to interfere because they get squashed into place by the components, so probably we could ignore that interference. And this final interference, I happen to know, is a deliberate mistake, which I've created in order to show you something later on. So again, I could ignore that. So I could come through and actually click ignore, and then these wouldn't reappear in the list if I carried on doing some work and rechecked. Something I hadn't mentioned earlier is component view. What this enables you to do is sort of flip it the other way up, so you can see the different components that are involved in interference, and then have a look at the interferences they are involved in. And this might help you identify a part which has a long list of interferences, then is the part you're going to want to concentrate on to fix, which I've already done by fixing my bolt. So that's interference detection. As I said, really nice way of identifying where there are interferences, and gives you a nice interface in order to isolate which ones you need to fix and which ones you can ignore. So the next item on the list is clearance verification. So if I choose clearance verification, it allows you to select a number of components. So I'm just going to select these two components. You can then choose the selected items. So are you going to check the clearance between the items I've selected, or between those items and the rest of the assembly? And then you get to choose what the minimum acceptable clearance is. So at this point, I want to see a clearance that is greater than 0.5. And then we can hit calculate. Now in this case, these two items are actually coincident. So we get the coincident interfering warning, which is what I was expecting. But I want to move down. So we can choose to show clearances we previously ignored. We can choose to treat sub-assemblies as components, exactly the same usage as before. We can ignore clearance equal to the specified value. So that's basically saying, at the moment, I want at least a clearance of 0.5. What this is saying is I want a clearance of 0.5 or greater. So it's quite, just a very subtle difference. Make parts understudy transparent. I think this is less useful in this particular tool, but if that's the way you like to work, that's absolutely fine. And again, you can create a fasteners folder to ignore all the fasteners. So let's have a look at some other items. So if I select these three items, again, let's have a look at the clearances between them. And I want to see a minimum acceptable clearance of 0.5. So if we click calculate, we've got two clearances coming up. We've got clearance 1, so there's stuff touching there, and then clearance 2, you can see there's a dimension on there showing a clearance of 0.25 mil between those items. If I shrink that down and said I want a clearance of at least 0.2 and recalculate, we only get the one where there's actually something colliding, if that makes sense. So it's very easy to sort of select your dimension, recalculate, and choose what's going to appear. So that's clearance verification. One last thing is, as well as parts, you can choose faces. So you could say, I want to know what the distance between that face and that component is, rather than the overall component. So that just be aware of that there. So there's obviously a collision between this. So that's clearance verification. Really nice tool. Really easy to identify what's going on where. This is sort of the static version of the dynamic dimension I showed you earlier in the move command. So it's quite a nice tool. We then move on to hole alignment. So with hole alignment, what it's doing is saying, going to check the hole alignment between the whole assembly. Again, I could select a number of components to check that the holes line up between them. Hole center deviation, the center of hole A and the center of hole B is going to warn me if there is a hole offline by 10 mil or less. If it's more than 10 mil, it's going to ignore it. For a part this size, you could probably bring that down to a much smaller value. Obviously, if you've got a big steel structure, you might want to bring that up. It might even be 20, 25 mil, depending on how much you trust your subcontractors to drill holes in the right place. I'm just going to hit calculate, and what it will do is, as we hover over them, it will highlight the features which are involved in that particular deviation. So this is 9.5 millimeters apart. There's a hole here and a hole here. Now, A, they're quite a long way apart, and B, axially, and B, they're quite a long way apart in terms of up to my 10 mil. So it's probably not going to be an issue. And the same is probably true of these items. We've got 5.4 and 8.57. Again, those are all very large distances for something which is relatively small, like my part is. So you might say ignore them. The only one which is of interest is this 0.4 mil, and this is actually doesn't highlight, but it's actually between the cut revolves within the arc of this orange component and the other one. Now that might be of interest because you would have thought that those would be centered on the same spot, so that might be something to go in and have a check. We could see we've got the cut revolve there, cut revolve there. So it's telling me the features which don't look aligned, so I might want to go and investigate that. Something that is of interest though is this hole is clearly less than 10 millimeters offset, but SolidWorks hasn't highlighted it. And that is because hole alignment is only true for holes where material has been removed. So that be a cut extrude, a cut revolve, or a hole wizard hole. Holes that have been created using extrude features, so boss extrude, boss base extrude, don't show up. And I've got another mini assembly which shows us that. So I'm just going to hop into that other assembly. So here we are, we've got two plates, exactly the same plate. Each plate's got two holes in it. If I do hole alignment for a gap of 10 millimeters or less, offset of 10 millimeters or less, and choose calculate, only one hole gets found, which is this one on the left. In fact, if I choose 4 or less, we find nothing, and that's because the gap between these plates is 5 mil. But why is it that only that hole is found? So we've got one hole here, and then this looks like a matching hole, and it doesn't pick it up at all. And the reason behind that is this: if we have a look at how our plate's been made, we've got a boss extrude and a hole wizard hole. Now the hole wizard hole is actually only this hole on the left. The hole on the right was formed as part of the boss extrude. So if I come through and have a look at the sketch of this, we can see the sketch for the boss extrude creates the hole as well. So the hole, and this is slightly weird terminology, the hole isn't a hole, the hole is an absence of material. So it's just something to be aware of with the hole alignment tool. It will only find holes which have been cut through material. It won't find gaps within your part that have been created by drawing a circle. So just be aware of that. It's quite a subtle difference, but it can be very important, particularly if you've got a large number of people working on an assembly. You don't know who's created holes in which fashion. But if you're intending to use hole alignment, then you will need to make sure that you actually cut the holes rather than sort of leaving them out when you extrude it to begin with. Right, so we'll now move on to the measure tool. The measure tool's probably been used by all of you in the past. It's a really nice tool, allows you to measure between A and B. And you can then say, if I've selected circular items like I have now, you can choose whether you're going center to center, minimum or maximum. Now, something that's new in 2013 is this point-to-point tool. Now, point-to-point tool does exactly what it says on the tin. It allows you to select a point and select another point, and it will measure between them. While you have the point-to-point tool active, even if you select circular items, so if I select these two edges here, it will only measure between the points I actually click. It won't allow me to check center to center, minimum, minimum, maximum, maximum. It will only do point to point. So just be aware of that. If this is grayed out and you can't click on it, you've probably got the point to point tool active. Also new in 2013, measurement history. Really helpful if you're trying to take a large number of measurements and then sort of use them in another calculation somewhere, for example, as opposed to having to measure it, write it down, measure it, write it down, measure it, write it down. SolidWorks now does the writing down for you, so you can get everything on one screen and scroll through the stuff you've measured before. So again, really handy. And then finally, we've got access to the sensor tool here. I'm not going to jump into it. I'm going to come to sensors in a second. Mass properties. Again, you've probably all used this before, but a couple of enhancements for 2013. We've got the create center of mass feature. So at the moment I'm looking at my assembly and I can see my center of mass is here. If I tick this box, when I leave the tool, it'll actually create a feature in the tree, right at the top of the tree as it happens, which shows me the center of mass, so I can see the center of mass while I'm doing other things. Obviously I may need to recalculate that center of mass if I add new components. We can also show weld bead mass. So if you are using a lot of welds in your assemblies, you can show the weld bead masses in here as well, which becomes really handy. Something to remember, I don't have to calculate the assembly mass. I can clear selections and I could select a subset of components, not only see where their center of mass is, but then see the mass properties for all of them. And one last thing that I forgot to mention, if I come up to the top and reselect the assembly again, it does show you down the bottom here that one or more components have overridden mass properties. So you can get to the override mass properties here and basically set a weight for a component or for a sub-assembly. And this menu does actually show you if there are any parts where that's happened. So battery housing, handle assembly, we know that battery housing's just had a weight set for it. So it just warns us here. We might want to check that and see whether that is actually what we want. So mass properties, few updates, still really helpful. We've got the sensor tool. Now I said I'd come back to this. Sensor tool, if you do simulation a lot, you'll probably have used this before, but we can use it just in assemblies as well, and it's still really helpful. So we've got a whole load of different sensor types: simulation data, mass properties, dimension, interference detection, measurement, proximity, relatively self-explanatory which does what. The mass properties is the one I think makes most sense at this top level assembly. We can choose to have a look at the various different types of mass property. For mass properties, there are a few. Obviously, if you select dimension, you just have to pick the relevant dimension. And at the moment, it's telling me the value is 15786. Now, yeah, big deal so far. But actually, what you can do is tell it to alert you, and it will notify you, say, if the value is greater than, let's say, 15500. Oh, I've got a couple of extra digits. And now when I accept this, I instantly get a yellow warning at the top and a yellow warning on the sensors. And that's because my mass is greater than the 1550. So this could be helpful if you're trying to keep weights down for the customer, or if you've got particular constraints. The other reason you might use it is you might say, right, I'm making stuff out of sheet metal or out of wooden board. I can choose dimension, then set the overall width of my part and the overall height of my part have got to be less than my standard sheet size in order to save costs, or because it just won't be manufacturable if it gets above a particular height. So that becomes really helpful, really easy to identify when things have exceeded your defined limits, if that makes sense. So give that a look. They're all really helpful. And now I have a look at Assembly Expert. Now, Assembly Expert is like a mini version of feature statistics. So it just gives us some information on the assembly. So we can have a look at the first line file. All the files to this assembly have been updated to the latest version of SolidWorks. Yeah, all well and good. But what's quite nice is if you've got some old 2012 files, it will warn you, give you a yellow X. I saw that when I was creating the assembly for this demo, for example. And it just warns you that that's going to take slightly longer to open and rebuild because it has to calculate it and then update it from 2012. Tells me the number of files in the assembly is 134. My large assembly mode comes on at 500, so it's off. Fairly standard, fairly obvious. There are 74 mates evaluated when the assembly is rebuilt, so it gives you an idea what's going on. If that number becomes really big, you will start to suffer performance. You will suffer a performance hit, so you might want to try and cut down or simplify those somehow. We can have a look at the rebuild time, so exactly the same as in feature statistics, and we can see that the full rebuild time is 136, the assembly rebuild was 128, the assembly features were 99, and the initial mate solve was 93 milliseconds. So we can get a nice idea of what happened where. If we scroll down a little bit more, we get a little sort of idea of how many components there are. So there's 134 components, of which 124 are parts and 10 are sub-assemblies. And we can see that although there are 124 parts, actually there's only 70 unique parts within the assembly. And we get an idea of some mates, bodies, how many documents are resolved, how many levels there are, so maximum depth. So that's top level assembly, sub-assembly part. So it's just, gives us an idea of how it's constructed, and then some details on where you can get some other diagnostic tools. So nice and simple. So that is assembly validation. There's lots of useful tools here on the Evaluate tab. They're all really handy. So thank you very much for watching. And if you need to get in touch for any questions, then feel free to contact us on the email or the phone number listed on the screen here. Looking forward, there's some future webinars. On the 8th of November, we've got design tables. 15th, we've got advanced surfacing. And 22nd, we've got routing and piping. So if you're interested in those, register for those on our website. Or if you prefer to wait till the morning, Luke will be popping out an email just before they happen. So look out for that.